4 human beings strapped themselves into the most powerful spacecraft ever built by human hands. They trained for years. They endured the weight of history pressing down on their shoulders. They carried with them the dreams of an entire civilization that has spent half a century staring at the moon and whispering, "When do we go back?" And they were told, not yet. Not because the rocket failed, not because the mission was scrapped, not because a politician made a decision behind closed doors or a budget was cut in some gray-walled conference room. They were forbidden from touching the surface of the moon because of something far older than politics, far colder than bureaucracy, something the universe itself wrote into the laws of physics long before the first human being ever looked up at the night sky. Artemis II is real. The crew is real. The Orion capsule is real. Its metallic hull polished to a mirror sheen that catches starlight in the absolute darkness beyond Earth's atmosphere. The space launch system that will hurl them away from this planet is real. A column of controlled fire and fury, tall enough to scrape low orbit before it even ignites its upper stage. Everything is real, except the landing. And when you understand why, when you truly understand the layers of danger, of physics, of biological fragility and cosmic indifference that stand between 4 human beings and the gray dust of the lunar surface, you will never look at the moon the same way again. This is not a story about failure. This is a story about what it actually means to survive space. The moon is 238,000 miles away. That number sounds manageable. You have heard it before. It fits inside a sentence. But distance in space is not measured in miles. It is measured in exposure. Every mile between Earth and the moon is a mile soaked in radiation that the sun has been hurling across the solar system since before life existed on this planet. Every hour spent outside the magnetic cocoon that wraps around Earth like an invisible shield is an hour of cellular bombardment that no spacecraft wall can fully stop. The Apollo astronauts got lucky. The science now tells us this with uncomfortable clarity. They traveled to the moon during a window of relative solar calm, stayed for hours, and returned before the sun had time to remind them how fragile human tissue really is. Artemis II will not land. It will orbit. It will swing around the far side of the moon, the side that has never once faced the Earth since the solar system was young. And it will come home. And that mission profile, that carefully calculated arc through the void, is not a compromise. It is a confession that we do not yet know how to keep human beings alive on the surface of another world. And that confession is the most honest thing humanity has said about space exploration in 50 years. Stay with this, because what comes next goes deeper than a mission plan. It goes all the way down to the physics of the sun, the biology of DNA, the engineering limits of the greatest machines ever assembled, and the terrifying question of whether human beings were ever meant to leave this planet at all. There is a boundary above your head right now that you cannot see, cannot feel, and have never thought about, because you have never needed to. It begins roughly 40 miles above the surface of this planet and extends outward for tens of thousands of miles into space. It is not made of metal or glass or any material that human hands have ever shaped. It is made of magnetism, of invisible force lines threading through space like the grain of some cosmic wood. And it is the only reason you are alive. The magnetosphere, Earth's magnetic field, a structure so enormous that if you could see it with your eyes, it would dwarf the planet itself. a teardrop-shaped bubble of electromagnetic protection compressed on the sunward side by the relentless pressure of solar wind and stretched into a long tail on the night side that extends millions of miles into deep space. You live inside this bubble. You were born inside it. Every human being who has ever walked this earth, drawn a breath, built a fire, written a poem, or loved another person, has done so entirely within the shelter of this invisible architecture. And Artemis II will leave it. That sentence deserves a moment of stillness. Because we say it so casually, leave Earth's magnetic field, as if it is simply a border crossing, as if it is a line on a map. But it is not a line. It is the difference between life and a slow, invisible death, written into the architecture of your own DNA. To understand what waits beyond that boundary, you have to understand what the sun actually is. Not the warm yellow circle that rises every morning and makes the crops grow and warms the skin and makes the whole enterprise of biological life on this planet possible. That is the sun as seen from inside the shelter, the sun as seen from outside. The sun as it truly is a thermonuclear furnace 864,000 miles across, converting 4 million tons of its own mass into pure energy every single second. It has been doing this for 4.5 billion years. It will continue doing this for another 5 billion years. And in the process of that conversion, it does not only produce light and warmth, it produces a constant, relentless storm. The solar wind is not wind in any sense you have experienced. It is a plasma, a river of charged particles, mostly protons and electrons, ripped free from the sun's outer atmosphere and flung outward in every direction at speeds between 200 and 900 kilometers per second. It is invisible. It has no smell. You cannot feel it on your skin, but it passes through ordinary matter the way water passes through a paper towel. Metal walls slow it slightly. They do not stop it, and beyond the solar wind, there is something worse. Solar energetic particles, SEPs, are the projectiles the sun launches during its most violent moments. When a coronal mass ejection tears through the solar atmosphere, when a solar flare erupts from a region of knotted magnetic field lines, the sun releases torrents of protons accelerated to a significant fraction of the speed of light. Not drifting, not flowing, moving at velocities that make the fastest spacecraft humanity has ever built look like a leaf floating downstream. These particles carry enough energy to penetrate spacecraft walls, to pass through the human body, to collide with the nuclei of atoms inside living tissue and shatter them. And then there is the deeper background radiation, galactic cosmic rays. These are not from the sun. They come from everywhere. They are the remnants of supernovae, the death explosions of stars, accelerated over millions of years to energy so extreme that physicists still argue about how exactly the universe creates them. They arrive from every direction simultaneously. They are ancient. Some of these particles have been traveling since before the solar system existed. And they pass through spacecraft hulls, through water, through lead, through the soft tissue of the human body, with barely a reduction in energy. Inside Earth's magnetic bubble, most of this is deflected. The charged particles curve away along the magnetic field lines, funneled toward the poles where they produce auroras, those shimmering curtains of green and violet light that people travel thousands of miles to witness. What looks like beauty from the ground is actually a collision. Radiation energy converted to light at the edge of the atmosphere. The magnetosphere is not passive. It is constantly working, constantly fighting. Step outside it, and the fighting stops. The Apollo astronauts crossed this boundary 12 times across 6 landing missions. The total time spent beyond the magnetosphere, in transit on the surface in lunar orbit, ranged from a few days to just under 2 weeks. The longest stay on the lunar surface by a single crew was 3 days. And even in those brief windows, the radiation doses accumulated. Some Apollo astronauts received doses comparable to hundreds of chest X-rays compressed into days. The ones who flew multiple missions carried that exposure cumulatively in their bodies for the rest of their lives. Here is the part that should make you pause. The Apollo program flew between 1969 and 1972, a span of 3 years that happened to coincide with a period of relatively low solar activity. The 11-year solar cycle that governs the sun's behavior was, during those missions, closer to its minimum than its maximum. The sun was calm by its own violent standards. The window was open. The astronauts slipped through it, accomplished something extraordinary, and came back. The universe did not notice them, and that indifference was their salvation. Now consider what a less fortunate timing would have looked like. In August of 1972, between the Apollo 16 and Apollo 17 missions, the sun produced one of the largest solar particle events ever recorded in the space age. A wave of high-energy protons swept through the inner solar system with enough intensity that it would have delivered a lethal radiation dose to any astronaut caught in open space or on the lunar surface. There was no warning sophisticated enough to provide meaningful evacuation time. There was no shelter on the lunar surface. There was no magnetic field to deflect it. If the mission schedule had been shifted by a few months in either direction, if Apollo 16 had launched later or if Apollo 17 had launched earlier, human beings would have died on the moon. Not from a rocket failure, not from a mechanical malfunction, from the sun itself, doing what it has always done, what it was doing billions of years before the first multicellular organism divided in the shallow seas of early Earth. This is not hypothetical catastrophizing. This is documented. This is physics. This is the specific reason why every mission architecture that attempts to return humans to the lunar surface must now contend with a problem that Apollo, through luck and timing, never fully had to solve. And Artemis II has not solved it. The Orion capsule has radiation-hardened electronics. It has water-filled panels in certain sections of the crew module that provide marginally improved shielding. It has protocols for a radiation shelter, a small, specifically reinforced area inside the spacecraft where astronauts are supposed to huddle during a solar particle event, reducing their exposure by perhaps 30% compared to the rest of the cabin. 30%. In a serious solar event, that reduction is the difference between a survivable dose and a catastrophic one. But survivable does not mean harmless. It means the astronauts will not die during the mission. It does not mean the radiation they absorb will vanish from their bodies when they land. It does not mean the strand breaks in their DNA will repair perfectly. It does not mean the cumulative cellular damage will not express itself years later as cancer, as cognitive decline, as cardiovascular disease. And this is where the science becomes something more than science. It becomes a question about what we are willing to ask of the people who go. Every person who has ever climbed into a spacecraft has accepted a level of risk that most human beings would find incomprehensible. They have signed documents. They have sat through briefings. They have looked at probability distributions and failure mode analyses and decided, consciously, deliberately, that the mission is worth the risk to their own bodies and their own lives. There is a word for this kind of decision. We call it courage. But courage does not change the physics. Courage does not stop a proton moving at half the speed of light from passing through a spacecraft wall and colliding with the nucleus of a cell in a human lung. The radiation environment beyond Earth's magnetic field is not a solvable problem with current materials. This is the honest truth that the engineering tells us. Lead shielding heavy enough to stop high-energy cosmic rays would make the spacecraft so massive that no rocket currently in existence could lift it. Water shielding helps against lower-energy particles, but provides minimal protection against galactic cosmic rays. Some materials, when struck by high-energy particles, actually produce secondary radiation, a cascade of lower-energy particles created by the collision itself, which in some scenarios can be more biologically damaging than the original radiation. The universe has, in a sense, set a trap. The heavier you make the walls, the worse the secondary radiation problem becomes. The lighter you make the walls, the more primary radiation gets through. There is an engineering optimum somewhere in that range, but it is not a solution. It is a compromise with physics that has already decided how the game is played. The Moon sits 238,000 miles from Earth, completely outside the magnetosphere, bathed in this radiation continuously. Its surface has no atmosphere to absorb particle energy. Its own magnetic field, what remains of it, is a patchwork of weak, localized anomalies, not a global shield. The lunar regolith, that fine, powdery gray soil that covers the surface, absorbs some radiation and could theoretically be used to construct shielding for underground habitats. But a habitat does not exist there yet, and building one requires humans to be on the surface for extended periods. The paradox practically writes itself. To build the shelter that would allow humans to stay, humans must first survive long enough to build it. This is the wall. Not a wall of politics or budget or technical ambition. A wall written into the structure of the cosmos, into the physics of charged particles and biological tissue, and the electromagnetic architecture of a planet that spent 4 billion years building the exact conditions necessary for life to exist in the first place. And the 4 astronauts of Artemis II will fly to the edge of that wall, orbit the Moon at close range, peer down at its ancient gray surface from a distance of thousands of miles, and then turn around and come home. Not because they lack courage, but because the universe has not yet given us permission to stay. The human body is not designed for space. This is not a poetic metaphor or a philosophical observation. It is a precise biological statement. Every system inside the human organism, the cardiovascular system, the skeletal system, the immune system, the vestibular system, the fluid dynamics of blood and lymph and cerebrospinal fluid, evolved under one specific set of conditions. One gravitational constant, one atmospheric pressure, one electromagnetic environment, one level of radiation exposure. Change any one of those variables significantly, and the body does not adapt. It degrades. We have known this for decades. We have watched it happen in real time aboard the International Space Station. In the bodies of cosmonauts who spent 6 months, 12 months, occasionally longer, in the microgravity environment of low Earth orbit. And what we have learned is simultaneously fascinating and deeply unsettling. Because the human body in space does not simply become weaker. It transforms. It reorganizes itself according to the new rules of the environment it finds itself in. And almost every reorganization it makes is one that will eventually kill you if you stay long enough. Begin with the most fundamental force you have never thought about, gravity. You feel it right now as the weight of your own body pressing down into whatever surface you are sitting or standing on. You have felt it every moment of your entire life. It is so constant, so absolute, so woven into every second of your existence that you do not experience it as a force at all. You experience it as normalcy, as the baseline of reality. But your cardiovascular system experiences it as an engineering problem that it has been solving continuously since the moment you were born. Your heart pumps blood upward against gravity to reach your brain. Your veins use one-way valves to prevent blood from pooling in your legs. Your lymphatic system drains fluid from your lower extremities back toward your core. Every blood vessel in your body has a tension, a tone, calibrated to the assumption that gravity is pulling fluid downward at exactly 9.8 meters per second squared. Remove gravity, and the entire system receives the wrong signal simultaneously. In the first hours of weightlessness, fluid shifts toward the upper body and the head. Astronauts describe the sensation as similar to hanging upside down. A persistent fullness in the face, congestion in the sinuses, pressure behind the eyes. The cardiovascular system, sensing more fluid in the upper body than it expects, interprets this as excess blood volume and begins shedding it. The kidneys increase urine output. The body literally shrinks its own blood supply because it believes there is too much. Over days and weeks, the heart itself begins to change. Freed from the constant labor of pumping blood upward against gravity, the cardiac muscle, like any muscle that stops being used the way it was designed, begins to atrophy. The heart becomes smaller. Its output decreases. Its walls thin slightly. And when the astronaut eventually returns to Earth and gravity reasserts itself, that atrophied heart must suddenly resume its full workload instantly, with no warm-up period, with no gradual reintroduction. The result, in some cases, is orthostatic hypotension. The blood falls to the legs faster than the weakened heart can compensate, and the brain, suddenly starved of blood pressure, threatens to go dark. Some astronauts returning from long missions cannot stand unassisted. They must be carried from their capsules. They must relearn, in the most literal sense, how to exist in the gravitational environment they were born into. Now place that same body on a journey to the moon and back. The transit time alone, just getting there and returning, is approximately 10 days for a free return trajectory like the one Artemis II will follow. 10 days of microgravity, 10 days of fluid shifts, cardiovascular deconditioning, bone mineral loss. And unlike low Earth orbit, where a space station has enough mass and structure to provide some degree of shielding, and where an emergency return to Earth takes hours, a crew traveling to lunar distance is days away from home. There is no abort option that brings you back in an afternoon. But the cardiovascular changes, significant as they are, represent only one layer of what spaceflight does to the human body. The skeletal system presents a problem of equal gravity, a problem that is, in some respects, even more alarming because of how silently it proceeds. Bone is not the static, inert material it appears to be. It is alive. It is constantly being broken down by cells called osteoclasts and rebuilt by cells called osteoblasts in a continuous cycle of remodeling that responds to mechanical stress. The pressure of standing, walking, carrying the weight of your own body. All of it sends constant signals to the skeletal system to maintain its density, to keep the scaffolding strong. Remove that mechanical stress, and the remodeling cycle loses its calibration. The osteoclasts continue their work. The osteoblasts slow theirs. The net result is bone loss, measurable, progressive, and not fully reversible even after return to Earth. In microgravity, astronauts lose bone density at a rate of approximately 1 to 2% per month in the weight-bearing bones. The hips, the spine, the femur. That is the rate of bone loss seen in severe osteoporosis patients on Earth, a condition that in elderly populations leads to fractures from minor impacts, to spinal compression, to a cascade of physical decline that fundamentally changes a person's quality of life. And it happens to young, supremely fit astronauts in peak physical condition simply because the gravitational signal that their skeletons depend on has been removed. Exercise helps. Every long-duration astronaut on the International Space Station spends 2 hours per day exercising specifically to combat this. Resistance training, cardiovascular work, load-bearing exercises designed to simulate the mechanical stress that gravity normally provides for free. It slows the loss. It does not stop it. And it consumes 2 hours of every day. 2 hours that could be spent on mission objectives, on science, on the 100 other tasks that a deep space crew would need to accomplish. On the surface of the moon, gravity returns, but not fully. Lunar gravity is 1/6 of Earth's. The mechanical loading on the skeleton is dramatically reduced compared to what the body requires to maintain its architecture. The famous footage of Apollo astronauts bounding across the lunar surface in slow, loping strides was not just a visual delight. It was a preview of a physiological challenge. On the moon, your bones are not receiving the signal they need. Your cardiovascular system is operating in a gravitational environment it has never encountered. Your proprioceptive system, the network of sensors in your muscles, joints, and inner ear that tells your brain where your body is in space, is receiving inputs it has never been calibrated for. And now add the radiation that the previous chapter described. And now add the next variable, one that researchers have only begun to fully quantify in the last decade, and whose implications are the most disturbing of all. The human brain changes in space. This is not metaphorical. This is not a reference to the psychological stress of isolation or confinement or the cognitive pressure of operating in a hostile environment. The physical structure of the brain, the white matter tracts, the fluid-filled ventricles, the delicate architecture of neural tissue, changes measurably in response to spaceflight. Brain scans of astronauts before and after long-duration missions show shifts in the position of brain structures. The cerebrospinal fluid that cushions and nourishes the brain redistributes in microgravity, compressing brain tissue upward toward the top of the skull and causing measurable changes in the volume and shape of the ventricles. Some astronauts return from long missions with a condition called spaceflight-associated neuroocular syndrome, SNS. The fluid pressure changes inside the skull affect the optic nerves, altering the shape of the eyeball and degrading visual acuity. Some astronauts who flew to the International Space Station and back found that their vision had changed permanently, not temporarily, not correctable with rest, permanently. The eye, the most exquisite optical instrument that evolution has ever produced, refined over hundreds of millions of years, was subtly reshaped by the fluid dynamics of weightlessness. Think about what this means for a mission to the moon and beyond. An astronaut whose visual acuity is degrading in real time, who must read instrument panels and navigate landing approaches and conduct spacewalks in a radiation environment that is simultaneously damaging cellular DNA. That astronaut is operating at a level of biological compromise that no amount of training can fully mitigate. And yet, here is where the philosophy of this situation becomes something almost unbearable in its complexity, because every one of these risks, the cardiovascular deconditioning, the bone loss, The fluid shifts, the neural changes, the radiation exposure. Every single one of them was known, documented, and accepted when the crew of Artemis II agreed to fly. They were not hidden from these four people. They were presented in full, in clinical detail, with probability distributions and worst-case scenarios and long-term health monitoring protocols that will follow these astronauts for the rest of their natural lives. And they said yes. This says something profound about the nature of the human animal, not about recklessness. These are among the most carefully considered decisions any human being can make, but about something deeper, about the drive that has been embedded in this species since before we had language to describe it. The same drive that compelled the first hominids to cross land bridges into unknown continents. The same drive that put boats on open ocean before there were maps of what lay beyond the horizon. The same drive that looked at the void between planets and thought, not I cannot go there, but not yet. Not with what I have right now, but eventually. The body is the limiting factor, not the rocket, not the budget, not the political will. The soft, water-filled, electromagnetically sensitive, gravitationally dependent biological machine that evolution spent 4 billion years building for a very specific planetary environment is the thing standing between humanity and the cosmos. And this is the deepest irony of the space age. We built the rockets first. We built the engines and the computers and the navigation systems and the life support architecture. We solved the engineering problems with stunning, almost reckless speed. In less than a decade, between 1961 and 1969, we went from putting a man in orbit for the first time to landing humans on another world. The engineering advanced at a pace that felt almost supernatural. But the biology has not kept up. The human body in 2026 is not meaningfully different from the human body in 1969. We have the same cardiovascular system, the same skeletal architecture, the same radiation sensitivity, the same dependence on gravity, the same neural wiring. The rocket science advanced by orders of magnitude. The biological science advanced by enough to understand the problem more precisely. And the more precisely we understand it, the more clearly we see the gap between where the engineering has taken us and where the biology can safely follow. Artemis II is, in one sense, a mission of extraordinary ambition. 4 human beings will travel farther from Earth than any humans since the last Apollo mission more than 50 years ago. They will swing around the dark side of the moon, that hemisphere of ancient craters and volcanic plains that has never once faced the Earth in the 4.5 billion years since the moon was torn from this planet's body in a collision of almost unimaginable violence. They will see with their own eyes what no living human has ever seen from that vantage point. And they will do all of this in a body that was designed for a world with a magnetic shield, a thick atmosphere, a gravitational field pulling at exactly 1 G, and a radiation environment that the sun is mostly deflected from reaching. They will carry that body into a universe that has none of those properties, and every hour they spend out there, the universe will be quietly, methodically, patiently working to undo what 4 billion years of evolution so carefully built. The mission will last approximately 10 days. The crew will return. Their bodies will have changed in measurable ways. They will undergo months of rehabilitation and monitoring. Most of the changes will reverse. Some will not. And the engineers and mission planners and flight surgeons who watch those astronauts walk or be carried out of their capsule will take the data, add it to the growing archive of what we know about human beings in deep space, and use it to push the next mission slightly further, slightly longer, slightly closer to the surface, because the goal the destination that all of this is aimed at, is not orbit. It is not a flyby. It is a permanent human presence beyond Earth, a foothold on another world. The beginning of something that has no historical precedent in the 4 billion-year story of life on this planet. And before that can happen, the biology has to catch up with the engineering. That is the race that no one talks about. Not the race between nations, not the race between companies, not the race between political visions of what space exploration should look like. The race between what human bodies can endure and what the universe requires of them if they are going to survive out there. Artemis II is a data point in that race. A precious, irreplaceable human data point. And the 4 people inside that capsule are not just astronauts. They are, in the most literal scientific sense, the experiment. There is a moment in the design of any spacecraft when the engineers stop asking what they want to build and start asking what the universe will allow them to build. It is the moment when ambition meets physics. When the dream of sending human beings to another world collides with the thermodynamic reality of what it takes to keep those human beings alive long enough to get there and come back. And in that collision, every compromise that has ever been made in the history of human spaceflight was born. The Orion capsule, the vehicle that will carry the 4 astronauts of Artemis II around the moon, is the most thoroughly tested crewed spacecraft ever built. Its heat shield is the largest ever constructed for a crewed vehicle, designed to survive re-entry velocities significantly higher than those experienced by Apollo capsules returning from lunar distance. Its life support systems were refined over decades of research. Its avionics represent the state-of-the-art in radiation-hardened computing. Its crew module volume, while modest by the standards of what 4 human beings actually need for 10 days of living and working, was optimized through an exhaustive process of trade studies and human factors research. And it is still, by any honest engineering assessment, an extraordinarily thin shell of metal and composite material between 4 human beings, one of the most hostile environments in the known universe. To understand why, you have to understand the fundamental engineering problem of deep space human spaceflight, a problem so severe, so deeply embedded in the laws of physics, that it has not meaningfully changed since the first engineers sat down to calculate what it would take to send a person to the moon. The problem has a name that sounds almost bureaucratic in its understatement. It is called the mass fraction problem, and it is the reason why every spacecraft ever built for human beings looks, from the perspective of what the passengers actually need, desperately inadequate. To launch anything from the surface of Earth into space, you need to overcome gravity and atmospheric drag. The energy required to do this is enormous. Not enormous in the casual sense of the word, but enormous in the precise thermodynamic sense. To place 1 kilogram of mass into low Earth orbit requires approximately 10 kilometers per second of delta V, the change in velocity that a rocket must provide. Every kilogram of payload requires a corresponding mass of propellant to accelerate it. And the propellant itself has mass, which requires more propellant to accelerate, which has mass, which requires more propellant. This recursive relationship, described mathematically by the Tsiolkovsky rocket equation, formulated in 1903 by a Russian schoolteacher working in almost complete intellectual isolation, means that the ratio of propellant to payload grows exponentially as the required delta V increases. To go to the moon and return, the total delta V requirement is roughly 20 kilometers per second, depending on the mission architecture. At the propellant efficiencies available with current chemical rocket technology, which remains the only technology capable of the thrust levels required for launch from Earth's surface. This means that the vast majority of the mass sitting on the launch pad on the day of liftoff is propellant. The space launch system that will launch Artemis II stands nearly 100 meters tall. It weighs approximately 2,700,000 kilograms, fully fueled. The Orion capsule and its crew, the payload that all of this engineering exists to carry, represents a tiny fraction of that total mass. This is not a failure of engineering. It is the rocket equation. It is mathematics. It is a constraint so fundamental that it applies equally to every space-faring civilization that has ever existed or will ever exist in this universe. Assuming any others do. Any intelligence anywhere in the cosmos that wants to leave a planetary surface against gravity using chemical propulsion will encounter the same exponential relationship between payload and propellant. The rocket equation does not care about the sophistication of the civilization that encounters it. And the consequence for human spaceflight is this. Every kilogram you want to add to the spacecraft, every additional centimeter of radiation shielding, every additional liter of water for drinking and hygiene and radiation protection, every additional cubic meter of living volume that would make the 10-day journey more survivable and less psychologically punishing, costs an exponentially increasing amount of propellant mass on the launch pad. At some point, adding protection makes the rocket too heavy to leave the ground. This is why the Orion capsule is the size it is. This is why the radiation shielding is as thin as it is. This is why 4 human beings will spend 10 days in a volume roughly comparable to the interior of a large SUV, sleeping in shifts, managing every bodily function in a microgravity environment with limited water and no privacy, and the constant background hum of life support machinery that cannot, under any circumstances, be allowed to fail. The engineers did not choose these constraints because they were indifferent to the comfort or safety of the crew. They chose them because the alternative, a spacecraft large enough and shielded enough and supplied enough to make the journey genuinely safe, does not exist within the laws of physics as we currently exploit them. The mass required to build such a spacecraft cannot be launched from Earth's surface with any rocket that exists or is currently in development. It would need to be assembled in orbit, component by component, launched on dozens of separate missions over years. And even then, the radiation problem, the galactic cosmic rays that no practical thickness of conventional shielding can stop, would remain. Consider the radiation shielding question in precise engineering terms, because the numbers tell a story that is more unsettling than any abstraction. The primary radiation concern for deep space travel beyond Earth's magnetosphere comes in 2 forms: solar energetic particle events and galactic cosmic rays. Against solar particle events, shielding is theoretically practical. High-energy protons from solar events interact with shielding material in ways that can be significantly attenuated by sufficient mass. Polyethylene, a plastic material rich in hydrogen atoms, is particularly effective because hydrogen nuclei are small and interact efficiently with incoming protons, absorbing energy and reducing particle flux. A few centimeters of polyethylene can reduce solar particle event exposure to manageable levels. But galactic cosmic rays are a different category of problem entirely. These are fully ionized atomic nuclei, iron nuclei, silicon nuclei, heavier elements, accelerated to relativistic velocities by supernova shock waves and other extreme astrophysical processes, and arriving from every direction simultaneously. When a galactic cosmic ray nucleus strikes a shielding material, it does not simply slow down. It produces a shower of secondary particles, protons, neutrons, pions, electromagnetic radiation, that in many cases delivers more biological dose to the tissue behind the shield than the original particle would have delivered on its own. This phenomenon is called secondary radiation or spallation. And it means that beyond a certain thickness of shielding, adding more material actually makes the galactic cosmic ray problem worse, not better. The engineering optimum for galactic cosmic ray shielding, the thickness that minimizes total biological dose, including secondaries, is surprisingly thin. Approximately 20 to 30 grams per square centimeter of material, which is roughly equivalent to the shielding that a few centimeters of water or polyethylene provides. Beyond that optimum, more shielding means more dose. The only genuine solution to galactic cosmic rays is not shielding. It is speed, reducing the transit time so that total exposure is minimized. Or it is biology, developing pharmaceutical or genetic interventions that make human tissue more resistant to radiation damage. Neither solution is available for Artemis II. The speed solution would require propulsion technologies that do not exist in operational form. Nuclear thermal propulsion, which has been studied since the 1950s and could reduce transit time significantly, remains developmental and unlicensed for crewed use. Ion propulsion, which is highly efficient but provides extremely low thrust, cannot accelerate a crewed spacecraft fast enough to matter for near-term missions. The biological solution is even further from reality. The mechanisms by which radiation damages DNA are so fundamental, so deeply embedded in the chemistry of living cells, that no pharmaceutical intervention currently known can meaningfully reduce the damage from high-energy heavy nuclei at the doses encountered in deep space. So the engineers built what they could build. They optimized what could be optimized. They built a spacecraft that will keep 4 human beings alive for 10 days in deep space, that will protect them from the solar particle events that can be predicted and partially shielded against, that will monitor their radiation exposure continuously and provide the data that will inform every crewed mission that follows. And they accepted that those 4 human beings will absorb a radiation dose that exceeds the career limits that regulatory bodies on Earth have established for radiation workers. Limits set based on decades of research into the relationship between ionizing radiation exposure and cancer risk. The astronauts of Artemis II will, in the course of a 10-day mission, absorb more radiation than a nuclear plant worker is permitted to receive in an entire year of employment. This is not a secret. It is documented in the mission planning. It is part of the informed consent that the crew signed. And it is a number that will increase substantially if the mission were extended to include time on the lunar surface. Which is why the lunar landing missions that follow Artemis II in the program's architecture will require solutions that do not yet exist at operational scale. Now step back from the engineering details for a moment and consider what all of this means at a more fundamental level. Humanity has built a machine of almost incomprehensible sophistication. A rocket taller than a 20-story building, an orbital service module capable of generating solar power and managing propulsion in deep space. A crew capsule equipped with the most advanced life support systems ever flown on a crewed vehicle. And this machine, for all its sophistication, is still fundamentally a thin-walled metal container filled with air and water and 4 biological organisms that evolved for a completely different environment, hurtling through a void that wants, in the most impersonal and absolute sense of the word, to kill everything inside it. There is something almost theological about this image. Not in any supernatural sense, but in the sense that it forces a confrontation with the scale of the challenge. The universe is not hostile to human life in the way that a predator is hostile to its prey. It is not aware of us. It does not pursue us. It simply maintains its physical laws with perfect consistency. And those laws happen to be incompatible with the survival of biological organisms without an extraordinary amount of engineering intervention. The vacuum of space is not cruel. It is merely empty. The radiation is not malevolent. It is merely energetic. The temperature extremes, 250 degrees Celsius in direct sunlight, minus 170 degrees in shadow, sometimes within meters of each other on the lunar surface, are not a trap. They are simply the thermodynamics of a world without an atmosphere to moderate them. The universe is not trying to stop us. It simply never designed itself with us in mind. And this is perhaps the most important thing to understand about Artemis II, and about every human spaceflight mission that has ever flown or ever will fly. We are not going to space because space is welcoming. We are going because the drive to go is stronger than the obstacles in the way. Because the species that evolved on this planet carries within it something that the planet itself cannot contain. A restlessness, an outward-pointing curiosity, a refusal to accept that the horizon is a boundary rather than an invitation. The engineers who designed Orion knew every limitation they were building into that spacecraft. They knew the radiation numbers. They knew the volume constraints. They knew the shielding compromises. They built it anyway, as well as it could be built within the laws that govern this universe. And the 4 astronauts who will climb inside it and allow themselves to be hurled into the dark on top of a column of fire. They know all of it too. They are not ignorant of the danger. They are not reckless in their disregard for it. They are doing something that is simultaneously the most rational and the most irrational thing a human being can do. Accepting known, documented, quantified risk in the service of a goal that cannot be measured in any individual lifetime, but only in the arc of the species as a whole. The spacecraft is thin. The shielding is inadequate by any absolute standard of safety. The body inside is fragile and gravitationally dependent and radiation sensitive, and built for a world that is 250,000 miles away. And it is going anyway. Because going is what we do. Because staying for this species has never really been an option. Because somewhere in the evolutionary history of this particular line of primates, the ones who stayed eventually gave way to the ones who went. And the ones who went found new worlds, new resources, new possibilities that the ones who stayed could never have imagined. Artemis II is that story told in titanium and carbon fiber and rocket fuel. It is the latest chapter in a narrative that began when the first human being looked at the horizon and decided that what was on the other side was worth the risk of finding out. The engineering is extraordinary. The spacecraft is extraordinary. And it is still not enough to land on the moon safely. Not yet. We have spent decades romanticizing the moon, and it deserves some of that romance. It is the most familiar object in the night sky. It has governed the tides of every ocean on this planet since before the first fish crawled onto land. It has been the clock and the calendar and the lantern of every human civilization that has ever existed. Poets have written about it in 10,000 languages. Lovers have stood beneath it in 10,000 cultures. Children have pointed at it before they had words to describe what they were pointing at. And it is one of the most dangerous surfaces in the solar system for a human being to stand on. Not dangerous in the dramatic, cinematic sense of volcanoes and earthquakes and roaring storms. The moon is dangerous in a quieter, more patient, more comprehensive way. It is dangerous the way a perfect vacuum is dangerous. Not through action, but through the absolute, uncompromising absence of everything that life requires. Every single property of the lunar environment that differs from Earth's environment differs in a direction that is lethal to unprotected biological tissue. There are no partial threats on the moon. There are no mild inconveniences. Every hazard is existential. Begin with the most obvious, the one that every school child knows and that almost no one has ever truly thought through. There is no atmosphere on the moon, not a thin atmosphere, not a trace atmosphere too sparse to breathe. The moon has what scientists call an exosphere, a collection of atoms so tenuous, so sparse, so far from anything that deserves the word atmosphere, that the space between those atoms is effectively indistinguishable from the hard vacuum of deep space. The surface pressure on the moon is approximately 3 × 10 to the -15 bar. Earth's atmospheric pressure is 1 bar. The moon's exosphere is 1 trillion times less dense than the air you are breathing right now. This means several things simultaneously, each of them fatal in its own way. It means that any liquid water exposed to the lunar surface instantly boils away. Not because the moon is hot, but because boiling is not about temperature alone. Boiling is about the relationship between vapor pressure and atmospheric pressure. At low enough atmospheric pressure, water boils at room temperature. At the pressure of the lunar surface, water boils at temperatures well below the freezing point of ice. The human body is approximately 60% water. An unprotected human body on the lunar surface would not freeze or burn or suffocate in any simple, singular way. It would experience all of these processes simultaneously, in a cascade of physiological catastrophe that would be mercifully brief. The absence of atmosphere also means the absence of any thermal buffering. On Earth, the atmosphere acts as a blanket, absorbing solar radiation during the day, radiating it slowly back during the night, moderating temperature swings to a range that liquid water and biological tissue can tolerate. The moon has no such blanket. In direct sunlight, the surface temperature of the lunar regolith can exceed 120 degrees Celsius, hot enough to boil water at Earth's atmospheric pressure, hot enough to cause severe burns through contact. In the shadow of a crater wall, or during the 2-week-long lunar night, surface temperatures can plunge to -170 degrees Celsius or colder. That is a temperature range of nearly 300 degrees between sunlight and shadow, sometimes within a few meters of each other, sometimes transitioning within seconds as an astronaut moves from a sunlit area into shade. No spacesuit currently in operational use was designed to handle that full temperature range continuously. The suits used during the Apollo missions, engineering marvels of their time, were designed for the specific thermal environment of the equatorial landing sites chosen for those missions during the specific lunar day conditions of those specific mission windows. They were not designed for the polar regions where future Artemis landing missions are targeted. Regions where the geometry of sunlight creates permanent shadow zones in deep craters, where temperatures at the bottom of those craters may never have risen above -250 degrees Celsius in the 4 billion years since they were formed. At -250 degrees Celsius, materials that are flexible at room temperature become brittle. Rubbers and polymers crack. Lubricants freeze solid. The mechanical systems of a spacesuit, the bearings and seals and joints that allow an astronaut to move, rely on materials and lubricants that were selected for their performance across a specific temperature range. Push them far enough outside that range, and they fail. Not gradually, catastrophically. The next generation of spacesuits, the Axiom spacesuits being developed for Artemis surface missions, incorporate advances in thermal management and materials science that address some of these challenges. But they are still suits. They are still human-scale engineering solutions to a planetary-scale problem. And they will still be tested for the first time in earnest on a surface where testing means risking the lives of the people wearing them. But the temperature extremes and the vacuum, as lethal as they are not the property of the lunar environment that keeps engineers awake at night with the most persistent, grinding anxiety. That distinction belongs to something that looks, at first glance, almost trivially mundane. Dust. Lunar regolith, the layer of pulverized rock that covers the entire surface of the moon, to depths ranging from a few meters to tens of meters, is not like any dust that exists on Earth. On Earth, dust particles are weathered. They are rounded and smoothed by wind and water and the constant physical abrasion of moving through an atmosphere. Billions of years of geological processes have worn the sharp edges off everything. Even the finest mineral dust on Earth has a texture that, at the microscopic level, is relatively smooth. Lunar regolith has never been weathered. There is no wind on the moon to round its particles. There is no water to smooth them. There is no erosion in any conventional sense. The regolith was created by billions of years of meteorite impacts. Rocks striking the lunar surface at cosmic velocities, shattering and vaporizing and recondensing into glassy, jagged, razor-sharp particles with surface areas so high that they carry enormous electrostatic charge. Each particle is a microscopic weapon. Each one is shaped at the nanoscale, like broken glass.